Let's see a demonstration of how to compute correlation, the different types of correlation, and how to perform the correlation test. I'm going to use the empty cars dataset where you have the mileage and vehicle specifications of different car models. Now, I am interested in the relationship between the MPG, that is the mileage, and the weight of the car, which is shown in the weight column over here. To compute the correlation between any two variables, what you do is use the cor function and pass the two variables to it. Here, these are the two variables, empty cars $mpg and empty cars $weight. This simply returns the correlation. Now, if you want to compute the correlation of every variable in the dataset against every other variable as a matrix, you could simply run cor and pass the entire data frame to it. Now here you can see the correlation of all the variables. In the first line itself, the correlation of all the variables against MPG. You can clearly see that cylinder, displacement, horsepower, weight, and the number of carburetors, these are all negatively influencing the mileage. While the other variables like the gear, engine type, DRAT, and QSEC, these are all positively influencing the mileage. Now, this correlation that we just computed is nothing but the Pearson's correlation. If you want to compute the Spearman correlation, set the method as Spearman and you will get the value. If you notice, the Spearman correlation is slightly higher than what we noticed for Pearson's correlation. That's because in Spearman correlation, instead of the actual value, you are computing the correlation between the rank of the respective variables. Instead of the actual values, the variables are replaced by their rank and then the correlation is computed. Likewise, Kendall's correlation also uses the rank underneath, but it has a different formula behind it. So you can see that the Kendall's correlation is slightly lower than what we observed for Pearson's as well as Spearman. Now there is something called correlation test. The COR function just reports the correlation value. But if you perform a correlation test, it gives some more estimates. It gives the p-value, the t-statistic, the 95% confidence intervals, and the sample estimate. Sample estimate is nothing but the correlation itself. Now, what this correlation test helps to determine is if this variable, that is whether the weight is a statistically significant influencer on the mileage column, MPG. So how to determine if it is statistically significant or not is if the p-value is lesser than a significance threshold of say 0.05. Typically the significance cutoff is 0.05. If p-value is lower than that number, then we infer that there is a statistically significant relationship. So what happens underneath is there is a null hypothesis established. Here you have the alternate hypothesis. Likewise, the null hypothesis is the true correlation is equal to 0. Now, the p-value helps us to decide whether the null hypothesis can be rejected or not. If the p-value is less than 0.05 or whatever the significance level that you have predetermined, if it is lesser than that predetermined statistical significance level, which is 0.05, then you will reject the null hypothesis. So this is almost close to 0. It's almost equal to 0. And therefore, you reject the null hypothesis that the true correlation is equal to 0 and take this relationship to be statistically significant. Now, what does this p-value even indicate? Like, where is this p-value coming from? Behind the scenes, R is fitting a linear regression model between mileage, we will take this as the y, as a function of weight, y as a function of x, where y is mileage and x is weight. From this, you are fitting a line of best fit. Suppose you have weight here and MPG here. The points are distributed something like this, suppose, and you are fitting a line of best fit. For this line of best fit, you are computing the beta coefficient. We will get to all of this when we are looking at linear regression as such. But understand that there is an intercept component and beta coefficient. Intercept is nothing but this term, this distance. When weight is 0, what is the value of the y? That is nothing but the intercept. I'm going to call intercept as alpha. So equation y becomes alpha plus this beta. Beta is nothing but the slope of this curve, the tangent of this angle. That is vertical line divided by this line, slope of the line of best fit. So that is nothing but beta, beta into x. So you substitute any value of weight in empty cast dollar weight variable. From this variable, you substitute any value of weight. The mileage can be predicted according to this equation. All right. So this equation is being estimated in linear regression. We have quickly covered linear regression as well in this quick discussion, but we will do that in a separate video if time permits, and we are going to attempt this topic. We will do that as well. Now, along with this linear regression, R reports the p-value of this beta coefficient. That p-value is nothing but this one, what we have over here. So null hypothesis H naught in this case is beta coefficient equals to 0, which is in this case is stated as the true correlation equals to 0. When correlation equals to 0, what does that mean? If correlation between these curve, if WT is here and MPG is here, if correlation is equal to 0, the points will be distributed something like this. There is no relationship. It is horizontal. This makes beta equals to 0 as well as correlation equals to 0, and that is nothing but the null hypothesis stated here, as well as in linear regression. This is the null hypothesis in linear regression model, and this is the null hypothesis where true correlation equal to 0 in correlation test, which is nothing but the same, because if the slope of the line is 0, the correlation is also going to be 0. Hope that is clear. Now let me quickly prove this to you. I'm going to quickly build a linear regression model, which you can build it using the LM function, where I am writing the formula MPG as a function of WT, data equals to empty cars. This is the linear regression model. I am going to view the summary of this. I'm not going to go into the details of how to interpret the summary of the linear regression model, but you can notice here the p-value written down here is this much, which is exactly the same as what we got in the correlation test output. So whenever you are computing correlation, this correlation test to help you quickly determine if the two variables have a statistically significant relationship or not.